This is, just as before, joint work with Dan Spielman and Nikhil Srivastava. So I'm going to start sort of where Nikhil left off. I might say a couple of things the same that he said, just to make sure that everyone's on the same page. But I'm really going to start from this problem in combinatorial linear algebra. But let me, I'll go over some notations and things first, just to make sure that you know what's going to happen. So I'm hopefully going to maintain these conventions. So D is always going to be the dimension of my vector space. When I have a letter without a hat on it, that's going to be deterministic. And when I have a hat on it, that's going to be random. And my main thing that I'm going to study are these random vectors, v1 through vn. So there are going to be n of them. And I'm going to use root as a synonym for 0 of a polynomial. So there will be a tree here, and I won't talk about the root of the tree. I'll talk about the top of the tree. So there won't be any, hopefully, confusion there. I want to say that I want to restrict all of my random vectors to having finite support. And then in my talk, all of the vectors are going to be real vectors, but the proofs will go through for complex vectors essentially just by replacing a t with a star. And just a couple of things to make you not have to think as hard. So all matrices, random or not, are going to be self-adjoint and positive semi-definite. So you can keep that in mind. And all of my vector products will be outer products. So I'm not going to do any inner products. So if you see two things multiplied together, you can think it's an outer product. So recall that when you have a vector, when you take this outer product, VV transpose, you get a rank 1 positive semi-definite matrix. And it has one non-zero eigenvalue, which is the squared norm of the vector. And it has a corresponding eigenvector that goes in that direction. So here's an example of that. The characteristic polynomial of a matrix is determinant of xi minus a. And I'm going to write lambda max of x for the largest eigenvalue of a matrix x. Okay? So the problem I'm interested in is, given v1 through vn, random vectors in d-dimensional space, independent random vectors, such that the largest eigenvalue of their expected outer products of the sum of the expected outer products is 1. And let's say that all of the vectors are small. Then what the conjecture is that there exists a function f, which is independent of n and d, n being the number of vectors and d being the dimension, such that the probability that lambda max of the sum is less than or equal to f of epsilon is greater than 0. And as Nikhil proved previously, this sort of implies Kadison-Singer by a series of works by Anderson, Borgan, Safriri, Ackerman, Anderson, and Weaver. So I'm going to establish some notation. So for random vectors v1 through vn, I'm going to talk about this theta function. And the theta function is essentially the best I could possibly hope for here, right? Sorry. So here there's a random, these are random vectors, but now I'm going to cheat, and I'm going to find the vectors which give me the absolute best situation for me. So I'm going to minimize the maximum eigenvalue of this sum, and I'm going to call that theta. And what our result is that if v1 through vn are random vectors, independent random vectors, such that the largest eigenvalue of the expected sum of the outer products is 1, and all of the vectors have a small size, then this theta of v1 through vn is less than or equal to 1 plus square root of epsilon squared. So essentially, you can always find some assignment of the vi's in the support of the vi's such that you get a largest eigenvalue of this size. So this should look familiar because it's exactly what Nikhil was talking about. So a couple of comments. Firstly, I want to mention that in this case, it suffices to prove this when the sum of the expected values of vi transpose is the identity, because this is really the hardest case, right? If our bound doesn't depend on n, then it doesn't hurt us to add in a bunch, add in more vectors to sort of fill in the identity. It's only going to make whatever we find worse than what we found before. So if we can prove this for the case when they sum to the identity, that's going to suffice. And as Nikhil mentioned, the previous result was due to trop, although it was essentially the same argument as Bourgain and Safriri, and used matrix concentration. And in that case, you get this theta of v1 through vn is less than or equal to something that depends on log d. So that's what we're trying to get rid of. And as Nikhil had mentioned, essentially any sufficiently generic concentration bound is going to depend on d. So we're going to have to abandon the hopes of getting a high probability bound, and instead we're going to have to try to find low probability events. And as he mentioned, the key idea is to switch from matrices to polynomials. So for any self-adjoint matrix A, the largest eigenvalue of A is the maximum root of its characteristic polynomial. Remember, the characteristic polynomial is that. And so for a random matrix A, the probability that the largest eigenvalue is less than or equal to t is the same as the probability that the maximum root of your polynomial is less than or equal to t. And so this suggests possibly studying random characteristic polynomials. And in fact, our first goal will be to show what Nikhil had mentioned, that this theta v1 through vn is less than or equal to the maximum root of the expected characteristic polynomial of the sums of the outer products. And just to be clear, because people sometimes have a double take, we're averaging the polynomials, right? Not the vectors of the matrices. Each matrix, well, each collection of vectors is going to give us a matrix. Each matrix is going to give us a polynomial, and then we're going to average those polynomials. So let's play along for a minute and do sort of a toy example. So what if we had A, a matrix, and I just wanted to add this random vector v, which either takes u or w uniformly. So if I was going to follow what I mentioned before about this characteristic polynomial averaging business, then what I would be interested in is this p of x, which is 1/2 the characteristic polynomial when I've added u, plus 1/2 the characteristic polynomial when I've added w. And already we sort of see one of the issues, and that's that the addition of that addition is a function of the coefficients. And we're supposedly trying to track the roots. And going from roots to coefficients is easy. You just multiply out the polynomial. But going from coefficients to roots is hard. And that's what Galois theory tells us. And in particular, you may not even have real roots. So here's an example of two polynomials where they both have two real roots, but when you add them together, all the real roots go away. So in particular, even talking about having an inequality comparing the roots of this thing to, well, anything else is sort of nonsense. But something really special happens in the case where we have root separation. So let the pi's be degree d polynomials, and st be a subset of R, an interval, such that all of the pi's are greater than or equal to 0 at s, all of the pi's are less than or equal to 0 at t, and each pi has exactly one real root in that interval. And the claim is that the sum has exactly one real root in that interval, and it lies between the roots of one of these guys and another one of these guys, pa and pb. And the proof is maybe a more mathematical picture, but you can see that the sum of so since all of them are greater than or equal to 0 at s, that means the sum is greater than or equal to 0 at s. Since they're all less than or equal to 0 at t, that means the sum is less than or equal to 0 at t. And so in particular, they have to be 0 somewhere. And then if you look at the point where it is 0, it's going to be the sum of something that has to be greater than or equal to 0 and the sum of something else, which is less than or equal to 0, and those will be the two polynomials that have roots that are on either side of it. And the comment is that if there happen to be d such intervals, then the sum over I pi is real rooted, right? Because each of those intervals is going to have exactly one real root of the sum, and the sum is a degree d polynomial, so it only has d roots. So all of the roots will be real. So this idea of separating intervals comes from, as Nikhil had mentioned, the study of interlacing polynomials. So if p is a real rooted polynomial of degree d, and q a real rooted polynomial of degree d minus 1, then, and with roots alpha and beta, then we say Q interlaces P if in between all of the alphas there's one beta. So here there's, you can track them, it goes pink and then blue, and then pink and then blue, and then pink and then blue, and then pink. So that's an interlacing polynomial. We say that a collection of degree D polynomials has a common interlacer if there exists a Q such that Q interlaces every PI simultaneously. So here the blue is interlacing both the pink and the orange, but you'll notice the pink and the orange themselves don't interlace. Right? They actually have, the orange has two roots close to each other, closer than the pink does, but blue still separates those roots from each other. So the way you can think of it is that the roots of Q are splitting up R into probably D intervals, each of which contains exactly one root of each PI. And so if PI has a common interlacer, then the intervals between the roots of Q are going to serve as our separating intervals. Right? So we'll be able to use the lemma. And in particular, it shows that this will be a real rooted polynomial. So back to our toy problem. Remember, our goal is to try to understand this sum of polynomials here. I'm going to make a definition which essentially just gives me exactly what I need in order to say what I want to say. We'll say that P hat forms an interlacing star with this collection Pi. If the average P is a convex combination of the PIs. Each of the PIs is a degree D real-rooted monic polynomial. And the collection PI has a common interlacer. Okay? And what is the corollary? Well, if the average P forms an interlacing star with the PIs, then there exists an I and a j such that the kth root of Pi is less than or equal to the kth root of the average, which is less than or equal to the kth root of Pj. So it's exactly just picking one interval of the D intervals that we have and using the lemma. So it turns out that this interlacing condition is kind of annoying. Having to do something separate in order to prove these things turns out to be a little more complicated than we want. But fortunately, we can translate this interlacing property to a collection of real rootedness properties. So this is a lemma that's old, it's folklore. It is in Fell, it's in Chudnovsky and Seymour. Let the collection Pi be a collection of degree D monic polynomials. The following are equivalent. Every polynomial in the convex hull of Pi has D real roots, and the collection Pi has a common interlacer. So we can get rid of this common interlacing condition and replace it with understanding when these polynomials have real roots in this convex hull. And if you remember, our equation, our P average is 1/2 of this plus 1/2 of that. What the lemma says is if we replace this 1/2 and 1/2 with lambda and 1 minus lambda, then what we would get is that we would get our common interlacer. And this maybe it should not be horribly surprising that this happens because the fact that we put a 1/2 and a 1/2 here is kind of artificial in the first place. I mean, I feel like if the 1/2 and 1/2 was a real root, there's no reason why you wouldn't think that lambda and 1 minus lambda would give you a real roots as well. But now, getting back to what our original problem was, remember we wanted to bound this theta function, which is actually a sum, which requires us to understand a sum of random vectors. So if it just so happens that the resulting characteristic polynomials, these 4 of them, all had a common interlacer, we'd be in good shape. Because then we could study this convex combination and then use our lemma to find one of these guys, which has a better root than the convex combination does. The problem is that this ends up being too much to hope for. Like, this is very, very rarely happens that you have all of your polynomials in your collection having a common interlacer. So instead, what we tried to do is to group them into smaller stars. And then the goal will be to iterate on this. So we call this construction here, this connected tree where each node forms an interlacing star with its children, we call this an interlacing family. And the punchline is that every interlacing family contains leaf nodes, p leaf 1 and p leaf 2, such that whatever root I'm interested in, the kth root, if I understand what's happening to the kth root of the top polynomial, I can always find a leaf that has a smaller root, kth root, than the top polynomial. And I can always find another polynomial that has a larger kth root than the top polynomial. And the proof is essentially what it is before. You start with the root that the polynomial you actually know, and you know that its two children have a common interlacer, so one of them has a better root than the one that you previously had, so you just move down the tree to it. Then you know, because this is an interlacing family, this polynomial's children both have a common interlacer, so one of them is going to have a better root than P1 did, and so you move to it, and you just keep going down the tree. Okay? So putting this all together, what we've done so far, we've shown that if there exists one of these interlacing families where the leaf nodes are all of the polynomials you can possibly get in the support of these random vectors, and which has the expectation over all of those polynomials as the top node, then what we would know is that theta of v1 through vn is less than or equal to the maximum root of the expected characteristic polynomial. Yes?
I have a question. So for previous cases, we don't need this tree structure because any convex combination of symmetric matrix is always symmetric. So it's always.
Yeah, but we're not averaging matrices, right? We're averaging the polynomials.
I see.
Okay, so yeah, I mean, we're going to need this tree structure. Like it's too much to ask for everything to have a common interlacer. So what do we need to do? We need to build one of these trees where all of the convex combinations of siblings are real rooted. If we can do that, then we've proved this lemma, and then we're happy. And this brings to what we call mixed characteristic polynomials. So for the rest of this section, let me call big V hat the random matrix that you get from adding the outer products of the random vectors. And I want to think about going down the tree like I'm going to be revealing the value of each of these random vectors. So the first one, I'll figure out whether or not random vector v1 was actually u or it was w. And then random vector 2, whether it was a or it was b. And the polynomials I'm going to have at each of these nodes are going to be the expected polynomial over all of the things that I don't know, given the things that I do know. Makes sense? And in particular, the siblings at depth t only differ in the value of vt hat, right? Any collection of children is just going to be the choice of some new vector after you already know all of the vectors that this guy knows. And it turns out that polynomials of this type can be written in a special form. So if v1 through vn are independent random vectors where the expected outer product is ai, then we can write the expected characteristic polynomial as taking this determinant of the sum of these matrices with some variables, applying this 1 minus partial derivative operator in all of the variables, and then setting all of the variables equal to 0. What you'll get left is something that only depends on x, and that will be this will be the expected characteristic polynomial. But what's important is that the expected characteristic polynomial doesn't really depend on the VIs themselves. It really only depends on the expected outer product. And that's sort of that's a consequence of being independent. You can imagine multiplying this whole thing out, and then the expectation just keeps going on into the inside. We call this a mixed characteristic polynomial, and we denote it mu of a1 through am. And what my claim is that every polynomial that we've seen in the tree is a mixed characteristic polynomial. The leaf polynomials, where we actually have a set assignment for the vectors, we can give those a really silly probability distribution where it's one with probability, where it's that vector with probability 1 and something else with probability 0 or just whatever. So the leaf polynomials are mixed characteristic polynomials. The top polynomial, which is the expectation over all of the polynomials, is a mixed characteristic polynomial. Now, rather than having any VI there, you have the expected matrix that you would have. And the middle polynomials are going to be exactly a combination of these, right? The ones that you know, you can give them a distribution where they are probability 1, the thing that you want them to be. And then everything you don't know, you give them their normal distribution, and then they will, and it will sort of fit this framework. What's a little more complicated to show, and I'm not going to show right now, is that every convex combination of siblings in the tree is a mixed characteristic polynomial as well. So if we can show that all of the mixed characteristic polynomials are real rooted, then we're done, right? Because this is exactly the condition we wanted, was to show that all of these convex combinations are real rooted, so this is how we're going to do it. So this brings about a question. How can one prove real rootedness without necessarily knowing the roots? Typically, you would want to know the roots to be able to test whether they're real. It turns out that a lot of people studied this question 80 years ago or 70 years ago when they were trying to solve the Riemann hypothesis, actually. And their idea was that maybe there are these transformations which, given a real-rooted thing, I can do this transformation, and what comes out is another real-rooted thing. And if I can understand those things, maybe I can show that the Riemann chi function is a transformation of something that I actually know is real-rooted. And if it's one of these transformations, then I'm in good shape. It didn't really turn out that way. And I should say that none of these, so there are a lot of these transformations that are known, and none of these really work on our polynomial. But fortunately, our polynomial, we sort of wrote it as a restriction from these multivariate polynomials. And recently huge gains have been made in extending real rootedness to multivariate polynomials. And this has been led by an effort of Borchea and Brandon in a series of papers, which really has developed this subject in an incredible way. So let me tell you what this extension is. So let D be a subset of the complex plane, be a domain. So a multivariate polynomial is called D-stable if it's either identically 0, that's sort of the default case, or it never has a 0 where all of its variables are in this domain. Okay? And the domain we're going to be interested in is H, which is the half of the imaginary plane, which is greater than 0. The imaginary part is greater than 0. And I'm just going to call those H-stable polynomials simply stable. So I don't have to write H every time. And if in addition all of the coefficients of P are real, then we'll call it real stable. So I apparently have problems counting. 3 important properties. Firstly, a univariate polynomial is real-rooted if and only if it's real stable. So this is a true generalization of real-rootedness. And this comes from the fact that if you have real coefficients, then your complex roots come in pairs. And so if you have any complex roots whatsoever, you in particular have to have one in the upper half plane. Okay, so not having real roots means that you're not real stable. The other things that are really nice are that if you have a real stable polynomial and you plug in some value r, some value that's a real number, then what comes out is a real stable polynomial. And if you have a polynomial that's real stable and instead of plugging in a value, you just sort of set 2 of these variables equal to each other, what comes out is a real stable polynomial as well. And I should mention this is very similar to hyperbolic polynomials. It's actually, they have very, very similar properties, and there's sort of a transformation that goes between the 2 of them. But for our purposes, these seem to be the better ones to talk about. And there are, just like I mentioned that there are these understandings of real-rooted polynomials and transformations that go between them, the same sort of things have been established for multivariate polynomials. So for example, if A1 through AM are Hermitian positive semi-definite matrices and X1 through XM are variables, then the determinant of the sum of the xiai is a real stable polynomial. This essentially comes from the fact that being positive semi-definite means that you have a square root that you can factor out. And then another lemma is that if P of X1 through Xm is a real stable polynomial, then this 1 minus partial derivative operation maintains real stability. Okay? So, cutting to the chase, the claim is that all mixed characteristic polynomials are real-rooted. And it really just comes directly from the formula, right? I mean, here we start with some sum of positive semi-definite matrices and take the determinant. So that's a real stable polynomial. We apply these operations one by one. Every time we do that, out comes a real stable polynomial. And then at the end, we set everything equal to 0. And plugging in a real number maintains real stability. So in the end, we have some polynomial, which we know is real stable because we used these real stability preserving operations. And it only has one variable, so it has to be real-rooted. So what is the corollary? It's that if v1 through vn are independent random vectors, then we can always find an upper bound on the best largest root we can get by looking at this expected characteristic polynomial. Any questions? Okay, good. So we've shown that we have this bound, but there's no reason, A, to think that this bound is any good. And B, there's no reason to think that this bound even is something that we can compute, because all we've done is compare this thing to some other thing that we don't really have any information about yet either. So let's talk about bounding roots, because now we're going to actually have to compute something. So rather than having roots that are points, multivariate polynomials have zero surfaces called varieties, right? So this is a bivariate polynomial, and this is the collection of points on which it's 0. And a degree D real stable polynomial has D varieties, and they partition Rn into D plus 1 components. So here this is partitioning it into 1, 2, 3, 4 components. And there are two components that are special, turns out. There's a positive one and a negative one. And how do you find the positive one and the negative one? Well, the positive one is the only one that contains a translation of the positive orthant. And the negative one is the only one that contains a translation of the negative orthant. And what's nice about both of these is that they're convex. And that's a property we'll use. And now if we look at restricting to a line this polynomial, that forms a univariate polynomial. And the restriction is going to have a real 0 every time this thing crosses one of those component lines. And in particular, if the line intersects both the positive and negative components, then its restriction is real-rooted. That's because if it crosses that and it crosses that, then it has to cross all of them, essentially. So recall a long time ago that I claimed that we could solve this problem in the case where the sum of these expectations is the identity. Here's where I'm actually going to use that, because it allows us to sort of transform our target polynomial into a nicer restriction like the ones that we had over there. And the transformation is essentially trivial, but the fact that it exists turns out to be a very nice thing for us computationally. So essentially, you just switch yi to zi plus x, and then this xi disappears. Except that now, rather than evaluating at 0, you're now trying to plug in x. So this defines a line in Rn that we're going to restrict to. So now in this new framework, remember we wanted to bound the maximum root of this expected polynomial in the case that the expected outer product sum is the identity and the expected norm of each one is small. In this new framework, what we're saying is that we want to find a t such that t times the all ones vector is in the positive component of this polynomial, this multivariate polynomial, whenever the sum over I of the AIs is the identity, and the trace of the AIs is less than or equal to epsilon. That's just an exact translation of that into this. And our idea is going to be to apply the operators iteratively and see what happens to the positive component. So we're going to apply an operator, something's going to happen to the positive component, we're going to figure out what that is, and then sort of add up all of these movements at the end. And to measure this effect, we're going to use what we call barrier functions. So the barrier function is the derivative in a given direction of the log of p of z1 through zm. And this is a generalization of a univariate barrier function that came from Batson, Spielman, and Srivastava. And it really sort of, you can get all of the insight into what this barrier function is doing by looking at the univariate case. In particular, on the positive component, each of these guys is monotone non-increasing as you go up, and it's also convex. And you can think of it as measuring the amount of cushion in the direction of zi. So it sort of tells you how close you are to the edge. If you sort of don't want to be on the other side. So I should mention that it suffices to consider bivariate polynomials. That's because essentially when one of these variables is changing, and we're looking at what happens to the barrier function in another variable, you can consider all of the other variables that aren't involved to be constant. So essentially, if we can understand what's happening on bivariate polynomials, we'll understand what's happening to all of these. So here is an example of some boundary functions. So this is when the barrier function is 2. And now here's where the barrier is 1. And there's where the barrier is 0.5. So you can sort of see, like, it tells you how far away you are. And here they are all together if you want to sort of see how they relate to each other. So now we're going to start applying these operators, 1 minus partial derivatives. And what's going to happen is two things. First of all, it's going to shift the entire component in the direction of the thing that you're taking the derivative in. And the second thing is that it's going to cause the region to sort of flatten inwards. You can imagine you're sort of hitting it with a baseball bat. It's going to move some amount because you're hitting it with a baseball bat, and so the amount of force is going to push this thing in this direction. But you're also going to indent this thing in a way that causes it to be sort of more, or I guess less round than it was before. So here's an example of this. So you can see that this thing has been shifted upwards, and if you look at this, it's kind of just a little bit more flat than, it sort of has less curvature than the original one did. So we're going to need to use these monotonicity and convexity properties to figure out exactly how far this went so that we can keep track of where these positive components are going. So the monotonicity lemma is that if P is real stable, and st is in the positive component of P, if the boundary function at the barrier function at st is smaller than 1, that means you're sort of far enough away from the edge, then after you do this operation, you're still going to be in the positive component. And you can see that here. This green line is the barrier function equals 1, and you can see that this, when I applied the operator, I didn't move far enough to sort of kill any of these guys who are in this zone. The problem is that we've also now changed the potential functions, right? Here I'm using the potential function in direction y in order to make arguments about what's happening. But when I do this operation in direction y, I'm also changing the potential function in direction x. So now I can't use that in the future if I need to use it when I sort of do my operator in direction x. So I'm going to have to compensate for that somehow. And the way we compensate is by making sure that we have just a little bit more cushion than we need. So what it says is that if P is real stable and st is in the positive component, and the barrier function is bounded away from 1 by some number, then that sort of tells us how much we can move in that direction to re-get our cushion back. Okay, so here's what's happening. I'm applying the 1 minus partial derivative operator. That's causing this blue line to go up. Then these are going to be my new barrier functions. You can see that we're not in, we've lost cushion because we're not inside the barrier anymore. But if we move this delta amount in the direction that we moved, in the direction that we took this operator, then we recover our original cushion in all of the other directions. And so now we're sort of in a situation where we're back inside the barrier that we need to be in, and we can iterate. Okay? So here's a proof of the bound. The goal of the theorem is to say that the point 1 plus square root of epsilon squared times the all 1 vectors is in the positive component of this thing. And you can imagine how it goes, right? So I start with my determinant polynomial, which I know very well what the positive component looks like. It looks like the positive orthant, right? Because these are all positive semi-definite matrices. So I could pick any t greater than 0 and sort of start that as my reference point. For now, I'll just keep it as t, and then we'll optimize at the end. So what's going to happen? I'm going to set my reference point to be w0. And then I'm going to compute the barrier function in all of the directions at w0. And it ends up being epsilon over t. This is where we use the trace of the AIs as small. So this gives us a value of delta where the cushion lemma is good. And so when I apply the first operator, 1 minus partial z1, I can move this delta in the direction of e1. And by the lemma, the new point that I'm at, w1, is still going to be in the positive component, is going to be in the positive component of this new polynomial. And it's going to have regained whatever this delta cushion was in all of the other directions. So now I have enough cushion that I can do this for 2 through m using the lemma at each time. And at the end, I've moved this delta amount in every single direction. So I'm going to end up adding that to whatever my starting reference point was. And what we've shown is that that, for any t, is in the positive component of the composite polynomial after we've done these things. And if you optimize over t, you get this 1 plus square root of epsilon squared, which is exactly what we wanted. So just to recap, we introduced a construction that we call an interlacing family of polynomials. We showed that every interlacing family contains leaf nodes p-leaf1 and p-leaf2, such that if I understand where the kth root of the top polynomial is, I can always assert that one of these p-leaf1 or p-leaf2 is on either side of it. Given these independent random vectors, we built an interlacing family where the leaf nodes were the support of these guys, and the top node was the expected value, the expected polynomial, which means that if I can bound the root of the expected characteristic polynomial, that would give me information about one of the leaf nodes, which is something in the support. And then we showed that the expected value of vi squared being less than or equal to epsilon, and that the expected outer product, sum of the outer products equals the identity, implies that the maximum root of this beast is always less than 1 plus square root of epsilon squared. So that tells me that I always have something that has, with probability greater than 0, a maximum eigenvalue at most 1 plus square root of epsilon squared. So I'd like to mention one application, which seems to be very nice. This is due to Ackman and Weaver using essentially our result. And what it says is that if w1 through wm are complex vectors, such that the sum of the wi star is less than or equal to the identity, which is the largest eigenvalue is at most 1, and all of these wi squareds are small, then for any collection of real numbers between 0 and 1, t1 through tm, there exists a set S such that when you add up all of the guys in S, the distance you are from this real combination of these guys is bounded by epsilon to the 1/8. So if you imagine that psi is this linear function which maps the ti's to the sum of the ti wi w star, di star, then what this is saying is that the image of the entire cube is well approximated up to some epsilon by the image of just the the corners of the cube. And this sort of screams out ideas in sort of, semi-definite programming relaxation, where you are trying to show possibly that when you solve a problem over this domain, which is something that you can do, you can assert that something in this domain is actually close to the solution that you get. And this is essentially saying that you can always do that. So this is some special case where essentially this is an integrality gap statement. And I wanted to mention some recent work. So I mentioned this idea of semi-definite programming and being close. So Nima Nari and Shayana Veskaran sort of use this idea along with about 1,000 other ideas to get improved bounds on the approximation algorithm for asymmetric traveling salesman. So previously, the known integrality gap was log n, and they were able to show that, in fact, the integrality gap was some polylog log n, which is much smaller. It's been used in a paper of Asaf Naor and Pierre Yosef in proving what they call improved restricted invertibility. So the idea of restricted invertibility is that you have a bunch of these vectors that behave well, but you have too many of them. And so you want to find some small subset that behaves well. And by well, I mean sort of they're as orthonormal as they possibly could be, or orthogonal to each other as they possibly could be. And Asaf and Pierre were able to show conditions on which you could get improved bounds on these things based on various properties of the original vectors. Another recent work is the existence of Ramanujan graphs of all degrees and all sizes. But I think probably even more interesting than that is the fact that there's a result of Michael Cohen, who is a grad student at MIT, which actually constructs these things from one of our things. So not only do we have existence of these Ramanujan graphs, we can actually build them in polynomial time. A number of improvements have been made. So sort of the ad hoc thing, so there were sort of two parts of this argument. One was showing that, something was an interlacing family, and then there was one that was bounding the actual polynomial. The first one is sort of turnkey. You just sort of show that something's an interlacing family, and you get this bound on any one of the things based on whatever your expected polynomial is. The root bounding was much more ad hoc and sort of required us to come up with these barrier functions that we were using to establish this thing. But in recent work, we've sort of come up with more general bounding techniques, which sort of given some combination of polynomials, tells you what the right bound on the combined polynomial is supposed to be. So I mentioned, that there was this huge literature about transformations which preserve real rootedness. The one thing they failed to do is to tell you where those roots go, apart from being on the real line. So these extensions sort of give general techniques that you can use. And they turn out to be related to free probability and sort of explain why these polynomials are actually good bounds. So, and it turns out that the method of interlacing polynomials, at least building the interlacing tree, is asymptotically tight. And so if you can get the correct bounds on whatever your expected characteristic polynomial is, you'll get whatever the best bounds you could possibly get asymptotically on the individual polynomials is. And there have been some extensions to higher rank matrices also by Michael Cohen, who's the grad student at MIT. So some open problems. One question is towards the computational efficiency of interlacing polynomials. Certainly we have one rendition of it, well, multiple renditions of it, where we can turn it into a polynomial time algorithm for finding these things. But we also have multiple renditions, including the Kadison-Singer one, where we don't know whether we can do it. It would be interesting for us to know what values of the AI cause the worst in terms of the largest root of this mixed characteristic polynomial. So it would have been way 1,000 times easier to just find the actual polynomial that maximizes this thing and then finding the roots of that thing, rather than have to go through this argument with the barrier functions that sort of like bounded all possible polynomials. And we conjecture that it's actually this, when AI is d over m times the identity, and that turns out to be exactly the Laguerre polynomial that Nikhil had been talking about. And if you remember, that had this 1 plus square root of epsilon squared as its largest root. So we believe that that's the answer, but we still can't prove it. And the last thing I wanted to mention was that, I mean, even maybe months before we were able to come up with our solution, people, well, so I'll just read. The general feeling in the community is that the original question, this is referring to Kadison-Singer, and therefore all equivalent forms have a negative solution. So Lotzi this morning was talking about where people were sort of anticipating the prospect that all of these characterization of finite groups was going to happen, and sort of developed, actually proved theorems based on the fact that they anticipated this being true. Well, this is not really the case here. I mean, nobody, at least a large collection of the population, really was caught by surprise by this answer, and so that leaves the possibility for a lot of sort of extensions to happen. I should say that Nick Weaver, in particular, did think that the answer was true, was positive. So he was one of the ones not in this community that thought it was negative. So thanks again to the organizers for inviting me. It's certainly an honor to be here, and thanks for your attention.